Okay, we are back, and in this video, I'm going to be talking specifically about Bayes' theorem and why Bayes' theorem is useful and what it's used for. Um, so what Bayes' theorem allows us to do is not only to calculate conditional probabilities, but to further condition probabilities on the basis of new information. So what we can do is we can sort of um, talk about, so the technical term is posterior probabilities, but we can further condition those probabilities as we gain new information or new evidence. So a lot of times you'll see Bayes' theorem written out in a way where we're talking about the probability of a hypothesis being true given our observations or our evidence and our background knowledge, right? And then you can keep adding, to those further conditions of evidence. Okay. Now, you also need to keep in mind that when we're talking about a conditional probability, um, whatever comes on the right hand side of the thresher stroke, that is a given. So the probability of A given B means B is a given. B is already accounted for. So what we're trying to figure out is to what extent, if at all, A is then further conditioned on B. So again, if the probability of A is equal to the probability of A given B, if those are equal, then B does not condition on A at all. That would mean that A and B are completely independent of each other. And the previous example rather I gave you of, you know, the probability of my failing to get pregnant given that I'm male compared to the probability that I'm going to fail to get pregnant given that I'm male and I take birth control. The fact I take birth control does not condition on this probability. So my failing to get pregnant is then independent of the fact that I take birth control. Okay. Now, the other thing that Bayes' theorem is useful for is it helps us navigate how exactly why a lot of our common errors in thinking about probability and statistics are incorrect or misguided. So this happens quite often. Okay, so suppose this is the case. Suppose the odds of against having an incredibly rare disease are 1 billion to 1. So if the odds against you having a rare disease are 1 billion to 1, that means the chance of you having this disease is incredibly low. It's very, very low. All right. Now, and let's say that symptoms of this disease include headache, blurred vision, fever, and body aches, and you have all of these things, right? You have all of these things. You have headaches, blurred vision, fever, body aches. You get on WebMD and you type in your symptoms, and this incredibly rare disease is the first disease that comes up. Okay, now, so given what you know, so you know that these are symptoms of the disease and you know that you have this disease. Given what you know, is it likely that you have this disease? So should you call your doctor right now and say, doctor, help me. I think I have this incredibly rare disease. The odds against me getting it are 1 billion to 1. Wouldn't it be a mistake to think that you have this disease? Okay, so think about it this way formally. Is the probability that you have this disease given that you have all of the symptoms? So the conditional probability, the probability that you have the disease given that you have all of the symptoms, is that greater than 50%? I mean, it should be clear that the answer is no. Here's why. What's the initial probability of D? The initial probability of D is incredibly low. So in order for the added information S to condition on D in such a way that it increases the likelihood of D to greater than 50%, that has to be some really good information with S. So now the reason why the presence of S, knowledge of S, knowledge of all the symptoms does not condition on D in this way is because we need to take into account this. We need to take into account probability of not having the disease and still having the symptoms. So take those symptoms, headache, fever, body aches, blurred vision. Aren't those symptoms of other things as well? Okay? So, I mean, if the initial chance that you're going to have these symptoms independently of any knowledge of any ailment or disease you actually have is 1%. I mean, your chances of having these symptoms regardless of having any known disease associated with them is already higher than your chances of having the disease on its own, right? And this is how medical diagnostics work. So we can't just say, all right, well, your symptoms are consistent with having this disease. And since the symptoms are consistent with having the disease, you probably have the disease. No. Why? Because these are symptoms of other kinds of conditions as well. And unless we eliminate those other kinds of conditions, so it's not enough to know that you have the symptoms. We would have to know that you have the symptoms and you don't have the flu. You have the symptoms and you're not, you don't have an infection. You have the symptoms and it's not any other kind of thing. Now, if we have the symptoms and we eliminate all those other possible conditions of which these symptoms are symptomatic, then come talk to me about maybe having this incredibly rare disease. But just because you have the symptoms and just because the symptoms are consistent with the disease, it doesn't follow from that that it's likely that you have the disease. I mean, we need to keep in mind the initial chance of you having this disease is incredibly low to begin with. So the information that we need to condition on that probability to even approximate towards 50% or above, to have a probability of 50% or above, we're going to need a lot more information than just the information contained in S. Now, but how many people do you know that will look up their symptoms on WebMD and think that they're dying? That's part of the problem here. We don't know how to reason about how probabilities and statistics and likelihoods work. Okay. All right, so let's use Bayes' theorem to go through an example here. Okay, so suppose you have a 15% of having strep throat, which is clearly a lot higher than the prior probability of you having this incredibly rare disease. Okay, and let's say that people who have strep throat test positive for strep throat 65% of the time. All right, so that 65% is a fact about the test. Again, it would be a mistake to say, well, I've got the prior probability or the initial probability of me having strep throat is 15%, but 65% of patients who have strep throat test positive, so my chances of having strep throat if I test positive are now 65%. No, that's not what this is reporting. Okay, so it is not the case that if you test positive, you now have a 65% chance of having strep throat. That's not how this works. Okay. Okay, so here's Bayes' theorem again. So the probability of A given B equals the probability of B given A multiplied by the probability of A, which if you will remember, that is the general conjunction rule. So the probability of B given A multiplied by the probability of A, and then that is divided by the prior probability of B. Okay, so let's plug in some values here. So we want to figure out the probability of you having strep throat given that you've tested positive. So we want to say, okay, well, given that we know you've tested positive, how does the fact you've tested positive condition on your having strep throat? Okay, so what's the probability of my having strep throat given I already know that I have a positive? That's what we want to calculate. Okay, so what's the prior probability of you having strep throat? The probability of A is 0.15, right? Now, and if the probability of A is 0.15, the probability of you having strep throat is 0.15, then the probability of you not having strep throat is 0.85. Okay, and then the chance of having a positive strep test, given that you have strep throat, like we said, is 0.65. So that would be the probability of B given A. The probability of having a positive test, given that you have strep throat, is 0.65, 65%. Okay. Now, what is the probability of B? So the probability of B is the prior or initial probability that you will have a positive test, right? So that's just the probability of having a positive test, regardless of whether or not we know you have strep throat. Regardless of whether or not we know you have strep throat, what's just the prior probability of the test being positive? Okay? So what that is, and this is what we need in order to calculate the prior probability of B. The probability of B is the probability that you have strep throat and a positive test, or you do not have strep throat and have a positive test. So the probability of B, just that you have a positive test, needs to take these two things into account. It needs to take into account the probability that you have strep throat and have a positive test, or you do not have strep throat and still have a positive test. Why? You can have a positive test regardless of whether or not you actually have strep throat, and that's what we're trying to figure out. Just what's the prior probability of you having a positive test? Okay, so written out formally, this is what it looks like. So the probability of B equals the probability of A multiplied by the probability of B given A, right? So that's the numerator. We already have that. So the probability of A is 0.15, the probability of B given A is 0.85, and then to that we add the probability of not A, so that's 0.85, multiplied by the probability of B given not A. Okay, now, and if it's helpful, you can read it out this way. So the probability of B equals the chance that I have strep throat and have a positive test. So A multiplied by B given A, right? So again, that's the general conjunction. Or the probability of me not having strep throat and having a positive test given that I don't have strep throat. Okay? So if it's helpful to think of the multiplication sign like an and, that's conjunction. The addition sign is disjunction. So that's you're basically calculating either one of those two conjuncts being true. Okay, so the probability of my having strep throat and having a positive test, given that I know I have strep throat, or the probability of my not having strep throat and having a positive test, given I know I don't have strep throat. Okay, so the probability of B needs to take both of those things into account. Now, and let's say that the initial chance or the prior probability of having a false positive is 0.25. So 25% of people that don't have strep throat will test positive. Okay. Now, you might be asking this, and this can be a little bit confusing. You might be saying, okay, well, wait a minute. If the probability of me getting a positive test, given that I have strep throat, is 0.65, then why isn't the probability of me having a positive test, given I don't have strep throat, 0.35? Right? Why wouldn't the probability of B given not A just be 1 minus the probability of B given A? Okay, well, the reason why this is the case is because these are not mutually exclusive possibilities, all right? Okay, and they're also not mutually exhaustive possibilities either. So this is the difference. There's a difference between a true positive, which is what the probability of B given A is. So the probability that I will have a positive test given that I actually do have strep throat. So my actually having strep throat is a given. So what's the probability that I will have a positive test given I actually have strep throat? Right? And then we have a false positive. The probability that I will get a positive test given that I don't have strep throat. So the two things we're taking into account here are only the true positive and the false positive. What we are not taking into account is the false negative. So a false negative is when you test negative for strep throat when you actually have strep throat. Okay, so true positive and false positive are not in any kind of way mutually exhaustive options here. So if my chance of testing positive given I have strep throat is 0.65, it doesn't follow from that that my chance of testing positive given I don't have strep throat is 0.35. So you don't calculate the probability of B given not A by just subtracting the probability of B given A from 1. Okay, that's a big mistake. So don't think that the probability of B given A and the probability of B given not A need to add up to 1. No, 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 no. They're not mutually exhaustive possibilities here. Okay, now, so if we plug in the numbers, this is what we get. So the probability of A given B, so the probability of my having strep throat, given that I have a positive test, equals 0.15 multiplied by 0.65. So the probability of A multiplied by the probability of B given A. And that's divided by the sum of 0.15 multiplied by 0.65 and 0.85 multiplied by 0.25. All right. So keep in mind that the numerator and the left-hand side of the denominator will always be the same. Why? Because they're the same probability. Okay. Okay, so 0.15 times 0.65 is 0.0975. So we fill that in for the left-hand side of the denominator. Okay. Now, and then 0.85 times 0.25 is 0.2125. Now, so the probability of A given B equals 0.0975 divided by 0.31. And when you divide 0.0975 by 0.31 rounded up, we get 0.31, which is around 31%. Okay. Now, so what does that tell us? Well, it tells us a couple things. So first of all, it tells us that a positive strep test increases the chance of having strep throat by 16%. Why? Because the prior probability of having strep throat is 15%. Now, but here's the problem. Notice that the probability of A given B is just equal to, approximately the probability of B. Right? So that 31% I rounded, but so the probability of A given B, so the probability of having strep throat given a positive test is pretty close to the chance of just having a positive test regardless of whether or not you have strep throat. Now, so how would this actually work in a real life scenario? So if my chance of having strep throat given I test positive are pretty close to my chances of testing positive regardless whether or not I have strep throat, that means we've got a really crappy strep test, right? So even if a positive test, or I'm sorry, even if you have a positive test, one positive test only increases your chances of having strep throat by 16%, and it's still only 31%. But that 31% is almost the same as testing positive regardless of whether or not you have strep throat. Now, so if we have data points that tell us this would be a clear indication that this is not really a reliable strep test. It like in real life scenarios, this would tell us that we've got a lot of work to do to improve upon our test. And to increase that value of 15%. So we went from 15% to 31%. To get closer to 50% or above, we would need to run multiple tests until we actually create a new test. Okay. Now, so what if we just did that? What if, so one test doesn't really increase the chance all that much to mean I ought to think I have strep throat, even if I've tested positive. So, if a positive test means you probably still should withhold judgment on having strep throat, again, that means you've got a crappy strep test. Now, but if we took a second test, given that I've already tested positive once for strep throat, if we take a second test, the values would have to change. Okay, so since I've tested positive, that means now the prior probability is 0.31, and then the probability of not having strep throat is now 0.69. So if the probability of A given B is 0.31, well, given that I know I have B, I know that the new probability of A is 0.31 based on that new information that I have available. Okay, now, but keep in mind, if we're running the same kind of test, the probability of B given A and the probability of B given not A are going to stay the same. Now, if we run a different test, we've got a new and improved test where the values of the probability of B given A and the probability of B given not A change, we're going to go back to that 0.15. But if we're running a second test of the same kind, the only probability values that are going to change are the probability of A and the probability of not A. Why? It's the same test. Okay? All right. Now, so do you see why it would be a mistake to go, oh, I tested positive, so now I've got a 65% chance of having strep throat, not given what we know about the test. So given that we know that the probability of having a positive test when you have strep throat is 65, and the probability of having a positive test when you don't have strep throat is 25, this is not a very good test, right? Okay, now let's run through another problem here and see how Bayes' theorem can help us. Okay, we're going to play a little game, and here's how the game is going to work. Suppose I have 10 plastic eggs, and I place a $20 bill in one of those plastic eggs. Okay. Okay. So, there are 10 players, and because there's 10 eggs, and only one of those eggs has a $20 bill. So you have a 10% chance of getting $20 in this game. Now, here's how the game is going to work. I randomly pass out the eggs, but when I'm passing out the eggs, I know which egg has the $20 in it, and I know which player ends up with that egg. So I already know who the winner is when I'm distributing the eggs. Okay. So I have the eggs, and I'm going to say, okay, it's this blue one right here that has it in it. And then I, just start passing them out. And then when I grab that blue one, I hand it to this person in front of me, and I say, okay, that's the winner. All right. So I know who has the winning egg. Now, but here's how the game is going to work. I am going to randomly call on people to open their eggs, but I am going to have the person who has the winning egg open their egg last. Okay? Otherwise, the game will be over too quickly. So, if I know you don't have the winning egg, I'm going to have the people with empty eggs open their eggs one by one so that the person with the winning egg opened their eggs last. So here's what happens. 8 empty eggs are opened in a row, and it comes down to you and one other person. So first there were 10 eggs, now we are down to 2 eggs, and prior to it being down to 2 eggs, what have we witnessed? We have witnessed that there are 8 empty eggs in a row. Okay? So what is the chance that you have the winning egg? It's down to you and one other person. So we started with 10, we are now down to 2. So don't we know that one of you is the winner and one of you is not? Sure. But is that the only thing we know? Now, if you're inclined to say that, well, my chances of winning are 50%, you would be wrong about that. Here's why. What was your initial chance of winning? 10%. Now, in order for your chance of winning to increase beyond 10%, doesn't something need to change? Yeah. Okay, well, what changed? You might say, okay, well, what changed is that all these other 8 people had empty eggs. Now, that certainly is true, but that certainly is true. It certainly is true that you have witnessed 8 people in a row open empty eggs. So that might create the perception that your chances of winning have increased. But isn't there information that you're not privy to, which if you were privy to, would change your judgment about your chances of winning? Yeah. Okay. So let's use Bayes' theorem for this. So we're going to calculate the probability of you having a winning egg based on the fact that we have new information, based on E. So what is E? So the probability of you winning given E is the probability that you have the winning egg given 8 eggs in a row are empty. So that's the observation that you've made. You've made the observation that it's down to you and one other person. We've got 8 empty eggs in a row. It's down to me and one other person. So I want to know what the probability of my winning is, given that 8 eggs in a row are empty. Okay, now but here's what's at stake here. In order for E to be relevant to W, it needs to be the case that the probability of you winning given 8 eggs in a row are empty is greater than the probability of you winning. So in order for E to condition on W, it needs to be the case that the probability of W given E is greater than the probability of W. So again, if the probability of W given E is equal to the probability of W, that means that E is irrelevant to W. E does not condition on W, okay? All right, so here are the values. The probability of W is 0.1 initially. So your initial chance of winning, or the prior probability of you winning, is 0.1, and the probability of you not winning is 0.9, right? So when the eggs are passed out, you got a 10% chance of winning, you got a 90% chance of not winning. But what is the probability of E here? What's the probability that there will be 8 empty eggs opened in a row? What is that probability? That's right. The probability of E is 1. It is necessary that 8 eggs in a row are going to be opened. Why? That is how the game works. If the person with the winning egg is going to open their egg last, then how many empty eggs are there going to be in a row? 9. So if it's a guarantee that the first 9 eggs are going to be empty, isn't it also a guarantee that the first 8 eggs are going to be empty? Yes. So since the probability of there being 9 empty eggs open in a row is 1, that means that the probability of 8 empty eggs being opened in a row is 1. Okay, so let's plug in those values. So if the probability of E is 1, then that means that the probability of E given W is 1, and the probability of E given not W is 1. What does that mean? So the probability that we're going to have 8 empty eggs in a row, given that you have the winning egg, is 1. Why? Because the probability of E is 1. Now, what's the probability that we're going to have 8 empty eggs in a row, given that you are a loser? Not, you didn't win. That's what I mean by a loser. That probability is also 1, right? Regardless of whether you have the winning egg or an empty egg, the probability that there are going to be 8 empty eggs in a row is 1. So the probability of E given W is 1. The probability of E given not W is 1. Now, when we plug in those values, this is what we get. So the probability of W given E equals 0.1 times 1, which is 0.1, divided by 0.1 times 1 plus 0.9 times 1. So 0.1 times 1 is 0.1, and 0.9 times 0.1 is 0.9. So 0.1 plus 0.9 is 1, and 0.1 divided by 1 is 0.1, which means that the probability of W is equal to the probability of W given E. So since the probability of you having the winning egg is equal to the probability that you have the winning egg given that 8 eggs in a row are empty is equivalent. So these are equal probable events. That means that E does not condition on W. So even though it's down to you and one other person, you've still only got a 10% chance of winning. Now, the game is designed to create the illusion. The game is designed to create the illusion that you're increasing your chances of winning each time an empty egg is empty. Now, but if you have an empty egg, the chance of you opening your egg first, or second, or third, or fourth, or fifth, or sixth, or seventh, or eighth, or ninth are equal probable. So if you've got an empty egg, the chance of you going first, second, third, fourth, fifth, sixth, seventh, eighth, or ninth is equal probable. You have an equal chance of opening your egg at any time. So the fact that it comes down to you and one other person is irrelevant in increasing your chances of winning. Why? Because the game is rigged. Now, but it would be easy for a lot of people to say, no, 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 my chances of winning are 50%. It can't be 50%. There aren't any relevant facts here that condition your chances of winning. There's information that you are not privy to that if you were privy to, right, would change the way you're calculating the probability. So if you knew the game was rigged, you shouldn't be impressed by the fact that it comes down to you and one other person. Now, if I didn't know who had the winning egg, and I randomly called on people to open their eggs, and we had 8 empty eggs in a row, and it comes down to you and one other person, and we still haven't found the winning egg, then your chances of winning are going up, right? But the whole reason why I'm calling on certain people to open their eggs is because I know their eggs are empty. So this is not like, the game Deal or No Deal where you could open the $1 million case with, at any moment with any pick. Like if I don't know where the winning egg is and I say, okay, hey Jerry, why don't you open your egg? And then Jerry opens his egg and he has the $20, and it's like, oh well, I had a half-hour time slot to fill on prime time on ABC, so the game's already over because we already found the winner. It wouldn't work that way. So if I want to extend the suspense, I'm going to be like, open your egg, and we're going to make it so that the winner opens their egg last. Okay. All right. So I know that's confusing and the math and the words and math combined with words and all of that. But once again, if you have any questions on any of this, do not hesitate to email me and I will see you all very soon.